Hello, this is part 3 for geometric similarity. And we're going to look at another example, this time to do with trees. So the first question is, are trees geometrically similar in general? And the answer is no, not really. But let's take a look at a few pictures just to see why that's the case. So here's some palm trees, for example. And notice we can see they're tall and skinny with a lot of palm branches at the top and otherwise nothing else. Compare that to an oak tree, and they look very different. So there's no characteristic dimension we could use where we could say an oak tree is a scaled version of a palm tree. And you might even ask, are trees geometrically similar to themselves? And for some species that might be true, but a baobab tree, it's hard to tell that even these are geometrically similar within each other because this one has such a very different look compared to some of these others. So let's see though if we can focus on one specific species that's maybe not quite as dramatic and try to get a model that will help us do something mathematically. So we're going to focus on one specific tree, and we would like to express the volume of it as a function of some characteristic dimension. Now, we're going to have some data here in a minute about black cherry trees, and we're given the diameter. So that's a good place to start. And we're also given the volume. So we'll call diameter D and volume V. And the question is, what's the relationship between volume and diameter? And as before, since diameter is a one-dimensional type of measurement, even though it goes around the tree, well, that would be circumference, but circumference and diameter are both one-dimensional. And so what that means is we expect volume to be equal to some constant times the diameter cubed. And so if we can find what this constant is, then we could potentially find the volume of any black cherry tree by finding the diameter, cubing it, and then multiplying by that constant. But let's see if that really works. So we need to go to the spreadsheet. Okay, so here we have the diameter and the volume of 31 trees. And so what we would like to do is find that proportionality constant. And just like we've seen before, we know that that constant is basically the ratio between the volume and the diameter cubed. So let me take volume and divide by this value cubed. And so the proportionality constant for this particular tree is about 0.018. We'll drag that down. And the good news is all these are about 0.01 something. The bad news is they're definitely not all the same. And so we are getting a model that is not going to be precise, but let's see if it's close enough to be useful. Now again, we don't know quite what is the best value, so I'm going to start with the average, as we've seen before, and see how well that works. So the average K value is about 0.01257. And so now we can construct a model from that. And so the model is just going to be that constant times the diameter cubed. We need a dollar sign next to the 1 because that number needs to stay constant. And now we can take a look at our data visually and see how well that works. Again, I'm going to use the control key to only highlight the cells I want. And then I'll insert a scatter plot. And if you like, you don't have to do this. This gives us a pretty good visual, but if we wanted to get a different look, we can change this to a smooth line. And if you wanted to spread out your data a little bit more, we could even range this from, say, 5 to 20, 22. But those are optional features. Now, we immediately see that we are really overestimating the data points for large diameters. So let's take this down a little bit. For instance, I could go half, right? We don't know how much, so if I go half, So if we go half, that's clearly going too far. If I split the difference, that looks pretty good for that data value, but I basically underestimate every other value. So I could try 0.01, a little bit better, 0.011. That's starting to be a little bit better. But notice we have the problem of, if you think about our residual analysis, is that no matter how we draw this line, we're always going to be underestimating some parts of the data and overestimating other parts, and those parts are basically going to be in two different parts of the domain. So if it was me, I would probably pick 0.011, but I'm still not satisfied with this model because there's definitely a trend to the residuals. So let's go back to our original assumption and see if we can do better. So keep in mind, this was assuming that all black cherry trees are geometrically similar. But as you might expect, if you had two trees that were the same height, that doesn't guarantee that they're going to be the same diameter, for example. But what if we assume the cross-sectional areas are geometrically similar? So what this means is that we're basically still assuming maybe trees are like cylinders rather than spheres. If you have an assumption like this, you're basically saying the trees are the equivalent of a sphere, not in shape, but in terms of how they scale. They scale only in one direction. But if you're assuming something like this, that is more like a cylinder, well, then you're saying a tree can both scale vertically and in terms of its diameter. So what this would mean is that volume is proportional to basically the cross-sectional area. So that would be diameter squared now, and then the height would be a separate dimension. Or in other words, V is equal to some new constant, we'll call it K2, times the diameter squared times the height. So this is a more sophisticated model because it has a second variable, height. And so naturally we expected to do a better job. And what we really need to ask is this enough better of a model that it makes up for the fact that we've made it in some ways twice as complicated, because now we need two measurements and height is going to be harder to measure than diameter was. So let's take a look at that, going back to the spreadsheet. Okay, so here we have our spreadsheet, and now we have the extra variable known as height. So I can calculate K2, which is just going to be volume divided by diameter squared divided by height. And we can drag that down. And once again, we have good news. It looks like they're all around 0.002. And as before, they're not all precisely the same. So we're going to have to estimate that K2 value. So we'll estimate that. And so we get about 0.002099. So let's try our model. And our model is just this value times the diameter squared times the height. And the F1 is a constant, so we need a $sign. I don't need all those decimal places, so I'll get rid of them. Now, we have two input variables here, so that's going to be a little harder to graph. So let's just do a input variable of d squared times height. So I will do this squared times height and drag this down. And then we can do the volume. And then we can do our model. Actually, what I'm going to do is, in case I want to change it, I'm going to just make this equal to that, and that way it will automatically change if I want it to. If I try to paste the formula, it'll change the cell addresses, which won't be great. So let's look at a plot of this. And so notice we get a more satisfying model. Now, can we improve on this? It's hard to tell because we don't seem to have quite the trend of the residuals like we did before. Here I have some are below, here some are above, above, below, above, below. This one's quite a bit on the mark. We could play around with this number a little bit, but honestly, I'm not sure which way I would even tweak it to make it more or less because it looks pretty good. Now, in future sections, we'll learn about more precise ways of measuring the validity of a particular model. But for now, this illustrates the point pretty well, so we'll leave it at this. So it looks like the best assumption for finding the volume of a tree was the cross-sectional area one, and we get a reasonable model. Again, depending on how accurate we need to be, you can see that the error, if we are interested in something like percent error, we could calculate that. Or we could do the model minus the actual divided by the actual, and then multiply that by 100. Again, we don't need a lot of decimal places. And again, we can see some back and forth, plus or minus. That's a good sign. There's some here in the middle that are a little bit more off, up to 18, 19%. But for something as simple as our model and as hard as trees are, especially when you think about some of those images we saw, for now, this is worth declaring success. So that's it for this section. We'll see you in the next video.